Thank you, everyone, and good morning in US on the East Coast for joining us for BrainX Community Live, the November 2020 edition. I know we have been through some of the challenging times in the recent past, but still there is a lot of energy and there are a lot of expectations for artificial intelligence implementation in healthcare. And I'm proud and I'm glad that Dr. Vidur Mahajan from India has joined us today. And we will be doing this special session, which is convenient to the Indian Standard Time and to the International Time for the first time, and hope we can serve our international community better too. So just to, for those who don't know about BrainX Community and have joined us for the first time, here are some introduction to BrainX Community. We formed with the idea of serving machine learning in healthcare for good. We have had 2 successful years. The community has grown up to be 2,000 plus international members strong. A few different locations for us. One is the website, which is brainxcommunity.com, which is a whole host of resources that I'll show you. And then a very active LinkedIn group, which shares a lot of scientific information and thereby developing collaboration. And we do these monthly live sessions over here, which are now available on YouTube in case you missed those. So the website has 3 key areas, the connect, the data, and the learn, which address the current needs for development of and application of AI in healthcare. The connect section, which used to be about us having monthly in-person sessions, has been online since the beginning of 2020 and has really flourished because of the unfortunate COVID circumstances. But you can find all the information and the link about these sessions that we do on a monthly basis with some of our guest speakers who are the real experts for application of AI in healthcare. As said, like we have our YouTube channel, so if you miss a session, you can always go and join us over there and watch the videos. There is a very active LinkedIn group. It's grown up to be 1,700 plus members strong. And then there is a learn section where we put in all the curated articles, which are again annotated for the different specialties that they belong to. So it's easy for you to search, and the links are there directly to the journals or to their relative web pages. And you can easily look at those articles which have been discussed a lot, curated, and are of interest to this community. And everybody is looking for data, so I'm very proud that we have created the largest repository of open source dataset links. So this section on our website has the direct links with brief introduction about all these different open source datasets, and you can go ahead and join us over there. Again, some more information about the datasets related to COVID-19. And last year, we launched the BrainX Community Europe, and the BrainX Community Middle East is going to be coming soon. We also created a journal section. So all the journals which are heavily engaged in AI application research, they are all listed over here. The meeting section, where you can find all the relevant and pertinent meetings throughout the year. Of course, this has been very dynamic this year because of the COVID-19 situation. And this has also fostered the transcontinental collaboration all the way with our friends in India. This particular paper that our team did over here, working with Dr. Topkadesh Sethi from IIIT Delhi, which is in preprint and under review, shows how this community has grown and fostered collaboration across continents. Again, some of the links to our resources are listed over here. But with that, I'm going to invite Dr. Vidur Mahajan. Dr. Vidur Mahajan is head of CARING. He is an expert in both imaging and artificial intelligence applications in healthcare, extremely well researched, He leads this amazing group which has been implementing AI in healthcare. There are a lot of us who have been researching AI in healthcare and trying to figure out how we can apply AI in healthcare. But he and his team has actually been at the forefront of implementation. And I always think of radiologists as being the leaders in this space who are applying AI in healthcare, not just researching it. And we'll learn a lot from him today. But the first question I have for Dr. Mahajan is about his background and what motivated him to look into artificial intelligence applications in healthcare. So thank you for joining us.
No, thank you, Dr. Piyush, for having me. And please call me Vidur. Dr. Mahajan just sounds too much. So, I think so. My background is I'm a physician and I'm a MBBS doctor, so I'm not a radiologist. But I did grow up in a imaging center. For anything else, like my family runs a chain of imaging centers in New Delhi, and because of that, medicine was kind of always the default uh, career path for me to go down. But that said, I always wanted to be a computer engineer. But then, in life takes certain turns and you make certain decisions, and I ended up going to medical school. Following which, I realized that my true passion lay in management and getting things done. Where I switched over, moved into management, started running our family business, started opening a few new centers, and in that process, I realized that I needed further education. So then went to the US, spent 2 years at University of Pennsylvania at the Wharton School, did an MBA there, and that was the year 2014 to 16 when deep learning started getting applied to medical imaging. So companies like Enlytic was founded in 2014, Zebra was founded in 2015. Again, Paras Lakhani's paper on chest x-rays came out in early 2016, late 15. So at that time, people started applying deep learning to medical imaging, and I was like, I have to be part of this stuff. So when I came back to India after doing my MBA, I started working, with as many AI companies as we could. So as an organization, whether it was through data curation, whether it was through algorithm, validation. Those were the very early days, right? Nothing really worked, and or if it was just general, for lack of another word, gyan, right? What should the company build? We started getting involved in that, and one thing led to another. And in 2018, we decided to formalize all of these efforts into what is today called CARING, the Center for Advanced Research in Imaging, Neurosciences and Genomics. A bunch of serendipitous things happened. So Dr. Vasant Venugopal, who's kind of my partner in crime, so he's a radiologist, extremely passionate about AI and 3D printing, and he happened to be working in our clinic as a part-time radiologist. And he would come in late at night, and I would leave by the time he would come. So we never really interacted. And then one day I randomly asked him, I was like, "Sir, what do you do during the day?" He said, "I work with some AI companies." I was like, "What is this?" so a series of things happened, and 2018 Caring was founded, and since then we've been trying to get our hands dirty, trying to get as many Docker containers as we can from as many companies across the world to truly run those algorithms on real clinical data and see what happens, which is what gives us a unique kind of perspective. But yeah, but that's the story in a nutshell, and I can keep talking, but uh, happy to
It's
answer
always
anything else.
interesting, how some of these incidents occur. It reminds me of how we founded BrainX with Dr. Pepe, who's actually on the call too. We just met together and we said, like, there is this great opportunity. We don't understand it that well, but let's start trying to understand it better. and that was the start of BrainX. And within 2 years, we started BrainX Community, which has grown to be 2,000 plus members strong.
Nice.
So it's always the people who have this interest, who build these communities around them, just like you have, and that promotes research and advances. So I'm glad you're leading this effort, not just for India, but for the world. And there is a great hope for this in the future.
No,
With
and
that, I'm
absolutely,
gonna stop
Piyush,
my
just
screen share and let you
sure.
start
No,
with your
I was just
presentation.
sure, absolutely.
Sorry, go ahead. You were saying something.
No, I was just saying that we also realized that India was very uniquely positioned, right? Because we of course, it goes without saying that we have some of the best clinicians in the world, and medical training and all of that. But on top of that, our disease spectrum that we have covers literally the entire world, because we have the higher socioeconomic strata all the way to the lower socioeconomic strata. So in terms of, so even from an AI perspective, almost all disease spectra are covered. So that was another unique again serendipitous advantage that we had, that generally, any use case that was being discussed anywhere in the world, clinical use case, we kind of had, something to offer on that. With that, I'll just share my screen and dive right in. Uh, cool. So basically, I'll spend the next, I think, 20 odd minutes, 20 25 odd minutes about talking about what it takes to implement AI in the clinic. And this is essentially, it's not a very straightforward answer. It's very much multifactorial, multifaceted. So there will be a lot of concepts that I will basically throw out. Feel free to ask me questions as I present. It's a small group, we can easily do that. And as candid or as direct as you'd like to be. I have no issues whatsoever, but it's going to be a lot of different concepts that I'll throw out. So of course, any talk on AI has to start with what is AI, and everyone, I think all of this stuff, most people on this call would know. But this is what I find most interesting. This is actually Tesla's theorem, and I found it on Wikipedia. And it says that AI is whatever machines can't do yet, because whatever they start doing stops remaining interesting, and hence it's not called AI anymore. Which is profoundly interesting, because if you think of a calculator, and if somebody had shown up with a normal accounting calculator some 50 years ago, people would have gone mad. That would have been the epitome of intelligence, right? Calculating the cube root of something to 10 decimal places in a fraction of a second would have been an intelligent task. Today we think of it as a calculation and not an intelligent task. So I truly feel that our aspiration as builders and users of AI should be to make it truly, truly dumb. So that nobody even thinks of it as being, something superhuman, or because till then it will not become part of our lives. And everyone has used AI. Many people don't know it. I'm sure this is a very educated crowd, but every time you use Google Maps, you're probably using one of the world's most sophisticated AI systems. Every time you use Swift key to type, or Google search, or any of these applications, you're using the world's most advanced AI applications, and many people obviously don't even know about it. This I'll spend some 30 seconds on this. There's two broad categories of AI applications, and this is the framework that I internally use, and I try to force my team also to use it, but they don't. But basically, there are things that humans can do, but machines can do much better or much faster, like monitoring CCTVs, cameras, translation. Humans can do all these things, but machines just do them much faster. And then there are things that humans just cannot do: multifactorial decision making, high dimensional data analytics, something like Google Maps, right? I can never tell you the exact time it will take you to go from point A to point B, but somehow magically Google Maps can do that. And that takes me to the next concept, where and this is very important from a healthcare setting, that tasks that humans can do but machines also do are explainable and are hence not magical in their nature, whereas tasks that humans cannot do but machines somehow end up doing magically, ends up, in that domain of magic. Now, of course, this is a spectrum. It's not binary, but at least, I like to think of this in terms of validation of AI techniques as they are coming into the clinic, because things that are not magical are easy to validate. Things that are magical, you'll have a very hard time trying to figure out whether it's truly working, or if it's just something else. So that's something to keep in mind. And AI is percolating into all aspects of healthcare. That's why this group essentially exists. Whether it's prevention and population health, diagnostics, therapeutics, AI is everywhere. So I won't go into that. And there are loads of FDA approved AI products out there. I think this is from last year. The updated slide would have even more products out there. And there are hundreds of companies building AI for medicine. Many people may have already seen this chart. This is from RSNA last year, when they basically put the logos of all the companies that were exhibiting. But still, there are challenges, right? And a deep knowledge of the challenges associated with AI is essential as you go out to deploy AI. And again, our singular focus for this talk is deployment. So just imagine you're trying to give a new technology to someone, give a new tool to someone. What are the challenges that you will face, right? You have to overcome those challenges first, and only then can you go ahead and deploy. So this is a summary of the challenges. You have to think about implications. There are technical issues, ethical issues, and then legal issues, and we'll quickly go through all of them. As I had promised, I will be bombarding you guys with concepts, and then you can bombard me with questions. So implications, right? What are the consequences of the AI that you are implementing, right? It's cool to think in terms of summary statistics, area under curve, sensitivity, specificities, whatever, Matthews, correlation, coefficients. But you have to also think at an N of one, right? Because your patient is a single patient. A patient doesn't have 100 instances and then you're right 99 times and wrong once, right? And hence your accuracy is 99. That doesn't happen in the real world. So what are the consequences of AI going wrong? How big of a mistake is AI making, right? Those kind of things are absolutely critical to think through as you go ahead and deploy these things. What are the clinical consequences? What are the commercial consequences? If I deploy a half-baked product in the at Cleveland Clinic, and it doesn't work, they are never going to buy my product again, and maybe half of the world will not buy my product again. So consequences need to be thought through very, very strongly, and not too many people doing this, because talking about negative consequences is a little bit of a gray area right now. But again, if you're thinking about deploying AI, do think about this in great detail. Just examples, right? This was our paper with the amazing team at Cure.ai in the Lancet. It was the first paper on AI in the Lancet. All the work done in India, amazing. 300,000 plus CT scans trained on, validated on, true independent data set of about 500 scans. Amazing area under curves, etc. But there was this one case where a infarct was labeled as a bleed. And as the clinicians would know that this can have catastrophic consequences if a human is not in the loop. So again, if this was unsupervised AI running somewhere, it could have been very, very bad. So just to drive home the point of thinking of consequences as you go ahead and deploy. The next is, this paper made a lot of noise about 2 years ago. AI can predict Alzheimer's more than 6 years ahead of diagnosis, right? And it was covered left, right, and center. Everywhere this paper was covered. And this was the paper behind it from Radiology, where a deep learning model predicts Alzheimer's disease using PET scans, right? And humans cannot do this, right? Humans can't. predict if somebody is going to get Alzheimer's disease 6 years in advance. So you amazing paper, but you dive into the numbers and you realize that it was a very small data set. It was just 40 cases, right? So the independent test set was just 40 cases, and out of that, it's true it had 100% sensitivity, but it had 6 false positives, right? And 6 false positives in this case means that these are 6 people who you told are going to get Alzheimer's in 6 years, but they don't get it, right? How do you rationalize that? What do you say to the patient? So again, great research, great algorithm, great intent, but if this was a clinical situation, what would happen? So just again to drive home that same point of thinking about implications. um, Similar work from MIT, again, great algorithm, predict breast cancer 5 years in advance. Again, magic, right? And you go deep and you realize that the AUC was actually zero point 0.7, and which is really not something that that you can trust in the clinical realm again. So great computer science paper, great intent, great model, but deployment ready, definitely not. And then of Stanford, we were like Matt is now a good friend, but theirs was one of the first papers, right, in 2017, where they said that now radiologists, AI is performing better than radiologists. And you read the archive paper, it says radiologist level pneumonia detection on chest X-rays with deep learning, right? This was the archive paper, and then a year later, the peer-reviewed paper came out, and the title changed, right? A retrospective comparison of the checks next algorithm. So from radiologist level, it became a retrospective comparison. So just again, not to demean the work in any way, because it is groundbreakingly amazing, but just to put in that point that it's important to read things in a little bit of detail and think about the consequences. Moving on to technical issues, generalizability of AI is a big question right now. Algorithms need to be tested on real world independent data. You need to know what was the algorithm developed on. Does it work on data from a different source? Does it work on data from a different country? Or does it work on totally unrelated data? Many times we've seen people put in random kind of photographs, like plant photographs, and it gives out a pneumonia score or something like that. So it's important to again be cognizant of the generalizability concept. And to kind of cover for generalizability, we wrote a paper on algorithmic auditing, where you can, it's a simple framework on how to go through validating an AI algorithm to make sure it works on your data. Explainability is another challenge. Why did the model say something, right? And Vasant wrote a paper on that. It's called Unboxing AI, where he tried to apply radiological insights to heat maps built by AI algorithms. So trying to figure out why AI is saying something. This is one of the hottest topics of research right now. I won't be surprised if many people on the BrainX group are actually working on this stuff. Our most recent paper was also on explainability. We proposed a metric for validation of true positives and true negatives, right? So true positives and true negatives are those cases where AI and radiologists agree, and typically nobody really looks at these cases because these are celebrated as successes. What we did was we started opening up those cases and started seeing is AI looking at the same feature that a human is looking at to call a case as positive or negative. And we got some very interesting insights. So anybody who's interested can check this out. Ethical issues are very, very hot. Nobody wants to study them simply because they're very difficult. Although recently there have been a few papers on this. Who owns the data, right? This is one of the biggest questions out there. We don't know the answer. As you deploy, you maybe need to know the answer, because you'll be sharing some kind of data back with the developers and all that stuff will happen. Is using free data sets okay, right? Again a question that's very much open. And can you make money from my data, right? Another very controversial and not talked about aspect of the whole AI revolution. And then there are legal issues, right? Who takes the blame for AI going wrong and who goes to jail for AI going wrong, right? Is it we are seeing this same issue play out in self-driving cars as well, where at one end you have the Google Waymo approach, where they say they don't even want to give you a steering wheel, and then you have the Tesla autopilot approach, where all the liability comes on the driver. So two extremes, and healthcare is going to have the same issues. And it's as of now, the verdict is that it's the doctor who has to sign off on the report, who takes all the blame or the credit for what goes on. I'll just quickly go through some deployment examples. This is the general radiology workflow. There's the patient scheduling and preparation piece. Then there's image acquisition. There's post-processing and analysis. So this is where the patient hasn't yet gone into the scanner. This is where the patient is in the scanner. This is, something happening to images that the radiologist has not seen yet. And then, diagnosis is the holy grail, which is where the where the radiologist looks at images and looks at the clinical information and tries to bundle it all into one, so as to, figure out what the disease is that the patient has. So pre-scanning, one of the most interesting use cases has been predicting waiting time, right? It's one of the, any radiology department, any hospital, I think, waiting time is one of the most sensitive and problematic areas. And there's work now that's been done at Mass General, and in fact this is from, I think, 2018, yeah, where they tried to predict patient wait time using multifactorial data. Very interesting work, relatively low risk. So you can still go ahead and implement many of these things. The other is, predicting hospital attendance. So the other way around, right? Will the patient even show up in insurance-based healthcare systems? This can be a problem. Somebody else is paying for the test. And my headache is no longer there, so I choose to not go. So again, they used various demographics and all. And I know that, and I think it is public information that DASA, one of the world's biggest radiology companies based in Brazil, uses such pre-scanning tools to optimize their workflows, which is very interesting, super impactful, and in terms of implications, it's just ideal, right? What's the worst that can happen, right? You're surprised that a patient shows up. So that's I like these kind of applications personally. um, Next, coming to the scanning domain, right, where you're tweaking something to the actual image. So this is work we did. Sounds very crazy to most radiologists. It actually is quite crazy, where we tried to create diffusion weighted images from T2 weighted images. So this is just an example where, this is an input T2 weighted image. So MRI scanners, the way they work is there's different types of uh, images that are acquired, using different types of physics parameters. And theoretically speaking, the images are totally different. But using, a GAN network and some very complicated things that I don't really know much about, we were able to take an input T2 weighted image and generate an image out of that image that's same as or similar to the true diffusion image, even from point of view of these subtle findings, right? So even this infarct here is picked up here, and this infarct it is not there on this image. Um, so very crazy idea, but it just to drive home the point of the role of AI in image acquisition. Post processing, automated segmentation is one of those things that is being now widely used. There are many tools. Most manufacturers have these built into their workstations. So, you see the liver, the vessels, the tumor mass, everything is automatically, segmented. This is from friends of ours at Credible in Bangalore. They built out this liver volumetry solution. And then, coming to the holy grail of diagnosis, where, again, this is our Lancet paper. So we're diagnosing disease on head CT scans. Then, this was our paper this was last year at RSNA, where we validated an algorithm that essentially creates text reports that are human-like from X-ray images. And we did a comparative study, and in fact, this won an award at RSNA for being the most popular AI paper, primarily because it talked about one, comparing AI and radiologist reports. So, that's always a hot topic. And the second is that, we talked about hedging. Because human beings are conservative, right? Nobody wants to really be blamed for overcalling a finding. So whereas AI doesn't do that. So AI doesn't hedge when reporting chest X-rays. This was a very interesting paper. But just to say that, it's there in diagnosis as well. It's important to know that deployment follows validation. So this is the, sorry, uh, yeah. So it's important to know that, deployment follows validation, wherein, and, we have this concept of triple A, where you first access, then you assess, and only then do you adopt. So this is an important framework to keep in mind. And this is our deployment architecture, what we use at Caring, wherever we go ahead and deploy our solutions, where, this here is the traditional hospital IT workflow. I've oversimplified it, but you have the modality layer, you have a PACS, and you have an RIS. And we don't touch this, right? We don't modify this at all. We simply put on another layer of AI that communicates with the existing systems. And then, depending on what type of deployment architecture you're using, images flow in, flow out, results can go from, one place to another, all through simple, network connections. We wrote a paper or poster on this at RSNA last year. And, I'll just actually, I think I have it here. So this was, practical guide for deployment of AI solutions in the clinical environment, how we do it. And, what we said was, there are three deployment architectures. This is fairly well known, and well established now. First is purely deployment on cloud, right? So if I go back to this diagram, these images need to somehow go to the AI algorithm. So the easiest or one of the ways is that these images go to a router that anonymizes and then uploads the images to the cloud. Then the AI does its magic on the cloud, and images come back, are de-anonymized, and then results go to the PACS or the RIS or the HIS, as the case may be. So this is cloud-based, right? You do need to anonymize the data. The data leaves hospital premises. You require very stable internet connectivity because everything relies on internet. But this is one of the deployment architectures. The second is an on-prem architecture where all the AI runs inside the hospital, right? So no data leaves the hospital premises. Generally, no internet is needed. You don't even need to anonymize the data. But one of the challenges is, why would an AI company that they've spent $20 million to build an algorithm give you their algorithm to put inside your hospital? Because it's very difficult to monitor them if they're not connected to the internet. That's one of the challenges. But we are seeing adoption in this realm to be the highest, where you go to a hospital, you tell them, I promise you your data will not leave your IT system, right? And that's an instant win. So that's why we have a bias towards on-prem inferencing. um, And then the last and maybe the ideal and the way of the future is going to be hybrid deployment, right? Where some AI runs inside the hospital, some AI runs on cloud. You can do dynamic and intelligent queuing, like if there's an X-ray model that needs, say, 10 seconds to run versus there's a coronary CT model that may take 5 minutes to run. The system is intelligent enough to figure out what to send to the cloud and what not to send to the cloud. And the end goal being that the radiologist, before they open the scan, sees whatever they have to see from the AI. So these are, three broad ways in which AI is being deployed. We did go a step further and build out a whole radiologist interaction system as well. We demoed this at RSNA last year, where this is, a typical US radiologist screen. They have the work list on one screen. You click a patient on the work list and images open up on two more screens. So we fully integrated our software into the PACS system to show how you can view AI results as a radiologist and then even go ahead and accept or reject them, before you can before they go to the PACS, because there's a bunch of legal issues there that I won't go into right now. But this is our human in the loop system, and we feel, at least today, this is essential, both from a medical, legal, and a safety standpoint. So this is how we approach the problem. These are, a few deployment examples. I'll quickly power through them. This is a lung nodule detection algorithm. So the old method, hard to believe in AI, there's already old and new. But in the old method, images would go from a CT scanner to a AI compute system, and from there to our PACS, and then the radiologist would see the images, and they would look like this, right? So this is your standard DICOM image, and you have the results of the AI literally hard coded on top of the image, right? So this is a image that has text in it, because it's just the simplest way to show something to a radiologist is to make an image out of it and just push it to their workstation. So this was the old way. The new way is where you generate you generate these editable region of interests, right? So you can literally have these boxes show up with whatever label you want, that the radiologist can change. There's a text box where all the results get populated. Again, those can be changed. And the radiologist has the power to accept or reject results. So this was, I think we were one of the first groups in the world, at least we were surprised that we were one of the first, but we were one of the first to figure out how to do this using DICOM. And Rohit from my team, I think he's on the call. He's the crazy genius behind all of this stuff. But makes life not only easy but also confident, or makes radiologists confident of AI. Um, Next, this is a very interesting story, and maybe we can close with that. This was a paper we presented at ECR, where we automatically pre-populated normal reports into radiologist reporting systems, right? So an X-ray chest is acquired, an image is received by the AI compute, and if there is no abnormality on the image, uh, an HL7 message, which is basically a way of communicating between these RIS systems. So the RIS system gets a message saying that this is a normal X-ray, and automatically a normal report is populated, right? This is when the AI thinks there is no abnormality. And if the AI thinks there is an abnormality, nothing happens. The radiologist reports the scan as they would in their routine workflow, right? And it had amazing performance, right? This was Cure.ai's algorithm. It had, we processed some 2000 X-rays through it, and 14 reports had to be changed. So we traced how many normals had to be changed by the radiologist. There were 12 misses, out of which only 2 were clinically significant. So in the scheme of things, the performance was amazing. But there was one very interesting behavioral aspect that we observed, which we were not expecting. So when we deployed this algorithm, we tuned it to always be right when it's calling something as normal, calling an X-ray as normal, right? Because so hence, we tuned it for extremely high sensitivity at the cost of specificity. And when you do that, you're essentially saying that I am fine having false positives. So normal cases being called abnormal, I'm fine with that because, anyways, my radiologist is going to look at those scans and he'll report or she'll report the normals as normals. But I am not fine having a abnormal scan reported as normal. Right. So once you understand that, and then just imagine with me, here's a radiologist who sees her screen and sees a normal X-ray there, but doesn't see the automatic normal report. And the AI is always correct, right? Because whenever the AI populates the normal report, it's always correct. So when it doesn't populate the report, in the human being's mind, the AI has seen something that I don't see. And then you nudge the person sitting next to you and you say, hey, do you see something here? I think this scan is normal. So something that would take 10 seconds to do ends up taking, 4 or 5 minutes. And we easily solve this problem by sending the normals and the abnormals to different people. But this was a very interesting behavioral thing that we saw, and I'm happy to talk about it, uh, you know, in detail. Another deployment example, right? These are super resolution algorithms. This one is from a company called Pixel Shine. You take a low dose CT scan and it makes a beautiful image out of it using deep learning. Again, these are probably the easiest to deploy because you really don't need any kind of integration on the RIS or anything. You just images come here, a secondary capture is generated, and you just send those images to the PACS, and that's about it. This is our work with the Subtle Medical out of Stanford. So so again they also take like a relatively bad brain MRI and up resolve them to make them give more detail. So this is how we do that deployment as well. And then this is another example of automated measurements, which is for spinal canal stenosis and a bunch of other things. So, in summary, there are challenges to AI deployment. There are regulatory challenges. There are data security challenges. There are, of course, performance challenges. One of the newer emerging challenges are algorithmic security challenges, right? We are presenting a paper at NeurIPS in the medical imaging workshop where we talk about um, taking a normal chest X-ray and almost impregnating disease in it, right? So we take a normal chest X-ray and you give it cardiomegaly, and then that same chest X-ray, it's still my chest X-ray. It has all the features of me, except it now has cardiomegaly, which it did not have before. So how does that play into algorithmic security as you think about building out your algorithms or using or deploying algorithms? So that's very, very interesting, and it's an emerging field right now. So in summary, each AI algorithm is different. Always think about the best integration methodology. Deep integration is preferred, but not always possible. So hence, keep experimenting. And pre-deployment clinical validation is key. You have to interview these things before you deploy them. So with that, I thank you for your attention, and any questions at all, I'd be more than happy to answer. We are actively recruiting. This is my shameless plug. We are actively recruiting across engineering, product, commercial. So, reach out to us if you find any of this stuff cool. Thank you.
Well, that was great, Vidur, and I think it was very insightful. Taking us across the different spectrums of AI deployment in real life, and I'm sure we are all thinking about all the different concerns that you showed, or the challenges that you showed. While there are questions that get populated over there, I actually have a question. What do you think is an acceptable accuracy? Because I hear about this chatter all the time, and I think sometimes it's a uh, different context for engineers versus us. They say, like, even if there is 1% inaccuracy, they don't feel confident about deploying AI. Whereas as physicians, we have seen these papers where the X-ray read by radiologists, by expert radiologists, can have up to 30% error rate, right? So if you have something that has inaccuracy of only 1%, isn't that way better than something that is going to be inaccurate 30% of the time? So how do you think about reconciling these differences where the engineer is trying to continuously improve upon something, but what's your end goal? What I kind of know part of the answer, but I would like your thoughts on that.
No, absolutely, Piyush. And this is so our paper on algorithmic auditing is actually precisely about this, right? And so the narrative is that an algorithm has, let's say, 1% error rate. Humans have 10% error rate. So why is AI not all pervasive, and why are we all not using it? It's so much better. I think the challenge is that the 1% error doesn't overlap with the 10% error. So what I mean by that, Piyush, is that you need to be very sure that a human will very rarely commit a blunder, right? So if you take 100 X-rays and show them to 5 radiologists, the mistakes would be overlapping because those would be the difficult cases, right, where there would be a mistakes. Whereas with algorithms, we have seen situations where these algorithms will pick up 1 centimeter nodules, sub-centimeter nodules beautifully, but discard the 5 centimeter mass because it thinks that's a pacemaker. So so that is the challenge, Piyush, that they need to be really really i- in sync, or there should be no blunders. And right now I don't think we are at in fact, our software CARPL essentially helps you find those blunders. Situations where AI was extremely confident that a finding exists, but in reality it does not. We call those cases as far north cases, right? So a high probability false positive. And then, we call other cases as far south cases, which are extremely low probability false negatives. Those are dangerous because, the AI was very confident that disease is not there, but disease was truly there. So that's the way we think about this until, we get like a spectrum in the middle, and, we don't have those far south and far north cases. It's going to be a bit of a challenge.
Well, I see a lot of excitement in this group, and this is a pretty international group. I see people from Middle East, from US, from a lot of different places. Kamal has a comment and a question. So Kamal, please go ahead.
Hi Vidur, hi Piyush. And first of all, it's amazing that you wake up in the morning, you are in a PJs, and you have an exciting talk to listen to. So that's amazing with the morning cup of coffee. Um,
Nice.
so I'm by way of introduction, I'm part of this BrainX group from Cleveland Clinic, works with Piyush in the Cleveland Clinic. And I call myself as a consumer of AI, not the developer. Consumer in a sense that I'm clinical trials, that's what we do. And we actually assess the performance of AI algorithms in clinical care on the outcome
Wow.
metrics, right?
Nice.
And that is one thing which you alluded to, that performance is not only mathematical modeling performance on based on your rock curves and everything. Performance is basically ultimately how it is actually affecting patient care, right? And in that, your performance measure actually changes. Then it become that, okay, what is the randomized trial which you can do to show that between humans versus AI, and then you show the value of it. So that's the kind of work which we are doing, not in the development phase. But in the same line, I just wanted to talk about um, one of the Indian market or Indian healthcare system. So in radiology, which your work is alluded to, amazing work, and the the outcome is in front of you, right? The diagnostics, like you have an algorithm built to diagnose, for example, lung cancer. An outcome is there. You
Yep.
confirm with the radiologist it's lung cancer, and you're done, right? But in other area of healthcare, outcome would be, did you have a heart attack? Did you have Alzheimer's disease?
Yes.
Right? And for that, you need a longitudinal record of a patient, right? And so what I'm trying to get at is like, how is the Indian market right now, where it is, knowing the healthcare system that electronic health records or population health records or the longitudinal records are not available for a particular person beyond what used to call it a slip, the medical slip. Everybody has this outpatient medical slip. So can you comment on that? How do you think that's going forward?
Absolutely. And thank you, Kamal. Off the record, I would love to show you our software, whenever you guys have time, because precisely that's what we do. But, so India is going through a very interesting phase of its, digital health journey right now, where, as of now, the patient, him or herself, is the longitudinal record. And by that, I mean there's that big polythene bag that typically, diagnostic centers such as ours give to patients, and then those become literally their health briefcase, right? And that's actually a treasure trove in itself, but that the patient carries around, and hence, comparisons are possible, and a doctor actually knows what's going on with the patient. The bigger health systems like the Apollos, Fortises, Maxes of the world, of course, they have very elaborate EMR systems. They track patients based on Aadhaar numbers, phone numbers, because for them, it's important to have that longitudinal data. The challenge is that India, being a market-driven healthcare system, I, as a patient, may go for an MRI scan to hospital A, for my consultation to hospital B, and then for my surgery to hospital C. And obviously, hospital A, B, and C don't talk to each other. But on 15th August, our PM announced the National Digital Health Mission, which is, this extremely ambitious goal of giving a unique health ID to every Indian citizen. Very similar to what they've done with UPI, which is the Universal Payments Interface, where every Indian person can now just do a bank transfer using their mobile phone. So they are creating a universal health ID, and patients create it themselves. And if you and on the other side, they're incentivizing healthcare providers to use this universal health ID, at least in their records. And then they're creating a middle layer of data fiduciaries that are able to connect various hospitals or healthcare providers. They literally call them data providers. They don't even call them healthcare providers. So they link various data providers so that when a patient goes from hospital A to hospital B to hospital C, doctors in hospital B are able to pull up records from hospital A. So it's a federated system, right? It's not a central cloud-based repository or anything like that. It's a federated system. So you're able to pull out data from hospital A, show it to a doctor in hospital B. Then similarly, when the patient goes to hospital C, everything is pulled out from A and B. So it's a fairly, complicated thing that is going to happen, but it has the Prime Minister's blessing, and it has super smart people working on, like Nandan Nilekani and those kind of people are kind of driving this on the tech side. So super excited about this playing out right now. Chandigarh and Pondicherry, few union territories are where it's being beta tested. But till then, uh, it's the patient who controls everything. So literally, if you could sit in an OPD and get those papers and scan all those papers, that would be a gold mine.
No, thanks for your comment. And it's amazing that this is going to happen at it's one of the biggest market, right? Biggest healthcare market. And we're building something on those lines. So I think we'll talk later offline. But thank you. Thanks for the talk.
Thank you.
Thanks, Kamal. I think that was a great question. You know what Kamal has been championing over here is the external validation. He just published a paper on external validation of AI algorithm in clinical workspace. It's available on BrainX Community. So congratulations on that, Kamal.
Nice.
We have a we actually have somebody from UAE, Avnish Khare, and he brings up a very important point, extending the conversation beyond the hospitals to the patients and the payers. And he put in as a comment where it's truly a question that how do you get all the three stakeholders, the payers, the providers, and the patients on the same page about AI? And I think it's a pretty broad question, but would love to get your thoughts on that, especially focusing on deployment of AI. How do you get all these three parties on the same page?
I think, what these three parties care about is essentially uh, either, cost reduction or outcomes improvement, right? And if you don't think of AI as AI, and if you simply think of it as a tool, there are various ways in which it would, you could bring all three stakeholders to the same to the table and get them to agree. In many cases, you may not even need them to, right? For example, on the image acquisition side, right? I talked about image acquisition. GE Healthcare is already embedding deep learning based image reconstruction. So, when you have a CT scanner, there's you acquire a low radiation dose CT, and then you apply deep learning to it to make it look like a high dose CT or a standard dose CT. So stuff like that, that is also AI. It's not the cognitive AI in terms of something that emulates human behavior, but it's still AI, and it's a no-brainer, right? You're reducing cost, you're giving the same kind of quality, and it's essentially driven by the equipment vendors. So I think the sweet spot is proving that there is some value. And then the second step is that value relevant to all three stakeholders, and then subsequently going ahead.
That's great. No, great thoughts on that. Here's an interesting question from Pushkar Agarwal. He's asking, the recent literature has shown that facial recognition models having some success in taking MRI images and reconstructing a facial image. So this goes around the security concern and allowing for identification of the individual patient. Have you noticed this security concern or have thoughts about this? And before you,
We wrote a paper on this that was rejected at like 3 conferences. So, and then now it's the hottest topic. So, we were kind of banging our heads. So it is very much a concern. There is absolutely no doubt that it is a concern, but it is of concern in uh, small data sets. So our experiment, what we did, we took some, I think, 15 people from our office, did super high resolution 3D brain MR, whole head MRs, did like a 3D recon volume render, and then showed those images to people who work with those people and to people who don't work with those people, and made like a like a match the following kind of exercise where you had to match the photograph to the face or the photograph to the MRI, and we showed statistically significant ability of people to match those scans. So that is true, but that is only true in very specific kind of scans, right? 3D T1 brain MRIs, or like high resolution whole head CT scans. Those kind of situations. And it's a concern. There are ways around it. There are scripts that will scrub the nose and do stuff like that. So that there are ways around it. I think the BRATS challenge, which is the brain tumor segmentation challenge, they've started using some of those tools, but yeah, it's true that you as imaging gets more high resolution, you're going to see more of the person who's being imaged.
yeah, no, and it's very interesting. Dr. Frank Pepe, who's the co-founder for BrainX, is here with us, and he's the chair for dermatology and plastic surgery and a prolific innovator, and has led the team that has done the face transplant over here. So he knows all
Oh,
about these facial recognitions. He was featured on National Geographic for leading the face transplants at Cleveland Clinic. which is just amazing process. So we think about that in real life, and then we think about how you can do that in the artificial intelligence space. It's really
Piyush, you
interesting.
bring about an amazing point. Like, if I could have like my MRI and your MRI, but make your MRI look like my MRI, and then somebody thinks that that's you, like, that's like second level
Right,
identification, which
right.
is very interesting.
Yeah. Well, I think we are at time. We could
Yeah,
do this all day long, but I think we had a
correct.
great discussion today, and would love
Yeah,
to continue this on future sessions. But if you have any other questions, feel free to put them on LinkedIn, or any comments, feel free to put it on the BrainX Community LinkedIn page. And Vidur, thanks a lot for a
yeah.
very exciting session today. Loved having you here, and a
Thank
great
you.
discussion from all the people who joined us from internationally, and spending our time with us. So thank you, everyone.